Hi, I'm Dave Robinson, and welcome to another one of my screencasts where I'll analyze data in R that I've never seen before. As usual, these datasets come from the Tidy Tuesday project, which is a really great project run by the R for Data Science online learning community. Every week, this group releases one dataset that's ready for analysis, and then I jump in and see what I can learn from it. So let's find out what dataset that we have this week. It's Chicago bird collisions, and this excites me. It's called nominative determinism. The Chicago bird collisions dataset comes from a paper from Winger et al. 2019. So who would have thunk it? So this is let's see. So we have is nocturnal flight calling behavior, vulnerability to artificial lights in migratory birds. This looks like some science, and then we have raw and tamed Chicago data. All right, important point. I'm not going to look at the spoiler. I think the spoiler probably tells some kinds of conclusions that maybe we can find ourselves from the data, so I skipped over that. All right, it looks like the two data sets: bird collisions, MP light. This data, using the data alone, the triad. Okay, I'm going to take a look at these two data sets. All right. Go to my repository, create a new RMD, and I usually start with library tidyverse. Time is, Start with library tidyverse, and I start by reading in the two tables. There's one bird collisions that has 70,000 observations, and what is that? 8 rows. 8 observations, 8 variables, 8 columns. And another is the light on each of those days. So it looks like I'll be able to join these two together, probably. I wonder if so that's immediately what I wonder is if I did a left join on MP light by date. I did a left join, maybe I'm going to make it a full join. And then I'm curious, filter is NA, are there any where, let's say, there is a light score but not collisions? Yes, there are. I don't really want that. It doesn't help me if I don't have any bird collision data. I'm going to make this a left join, but there might be cases where we don't have a light score. All right, how many? 28,000. Okay, so that tells us, let's see, I wonder when we have a light score and when we don't. I can start just by histogramming it. Say histogram the date, geom histogram, and fill equals is NA light score to find out where the missing data is. Yeah, it looks like we didn't have any light score data before 2000, and now we usually have it except for a few times where it seems to be missing. So this line we know is mostly light score data we only have from that time period. Now I have to find out what light score means. Does that mean how good the visibility was? It's the number of windows lit at McCormick Place, Chicago. So probably looking for McCormick Place. I really don't know Chicago that well. Is this whether the recording is at McCormick Place or Greater Chicago area? So I didn't really look at this data much yet. But is this every single? Is every one of these a bird dying? That's dark. Let's see. So we have looking through just to figure out. I guess so. There's a bird genus and species. There's a date. Okay, so did it collide with another bird or did it collide with I'm trying to understand this. Collisions with lighted structures. Okay. I'm sorry, it's not interesting to hear me read it. Okay, my guess is this is the story of a building called McCormick Place, and the question of how often birds fly into it and die. It looks like we have two localities. This is the McCormick Place or generally in Chicago. I'm curious how that breakdown, what that breakdown looks like. If I change this to be fill locality, I'll see what's the general breakdown and how does it change over time. Okay, the McCormick Place, we've had McCormick Place data for a long time, and we've only had light score in a more recent period. And we've also only had the Greater Chicago area in a recent period. Okay? It also does look, what's interesting is that the McCormick Place ones seem to be generally trending downward. Don't know if there's anything to conclusion to draw from that. All right, and we have a couple other, are these categories? Yeah, all these are factors. Well, all of these are factors except for date. So there's a lot of things that might influence, say, the rate of birds dying. Certainly, certainly the thing is we don't have a baseline data set. I don't actually have the ability to say, I can't say, well, these are the most common birds. So I can't say, I'm going to show this. I'm going to show what the most common types of birds are that die that collide by genus and by species. But I'm not going to be able to take that and say, oh, therefore those are species that are less able to avoid obstacles, because we don't know if that's entirely representative of the background population of birds. I have an idea of how we're going to test this hypothesis, but we're going to have to get to it in a little bit. It's going to involve these light scores. It's probably what the paper was looking at, though I probably won't have the time and the expertise to go as statistically sophisticated as they, I imagine, did. Okay, so so if I take a look at my collisions, I'm going to leave in a left join. I'm going to do that right here. Good. I'm going to, here's my locality. I have a lot of factors in this data set, a lot of categories. So I'm going to visualize them one by one. Every time I visualize, I start with a count, then a head, then a ggplot. I missed a step, actually. I'm going to come back and do that. Bar plot, coord, flip. It's a solid enough graph, but it's not going to be ordered the way that I'd like it to. So I'm going to start with, let's see. I'm going to start with genus equals FCT reorder the genus by n. That part I can do. I can say these are the most common genus. But I actually realize I'm going to do that with a lot of different factors, and I want to get a feel for this data really fast. I don't want to keep copy-pasting this code. I could, or I could write a function, but I've got a different idea. I want to look at my 1, 2, 3, 4, 5, 6 factors at the same time. How can I do that? I can do that by changing the way the data is shaped. I can gather them. I can say I want a what do I call it? Category value. And I want it for genus, species, actually literally I want it for everything besides date and light source. Light score. So now I have my date, my light score, my category, my value. And now I can count category and value. I can even group by category, top n, 16 by n, get the top ones from each, plot it as basically the same thing that I'm doing through the rest of this. I am going to need to hope that there's no levels that occur in one factor that also occur in others that could mess up some of these bar plots. But I'm not explaining what I'm doing right here. Sorry for that. The trick here is I'm building up to a facet wrap by category, and a count value instead of counting genus. Let's see how that worked out. Oh, I forgot an important step. Scales equals free. I think when you flip it, it's free y. Am I right? I am right. All right. So what I just did is say I want to know what each of these categories looks like. I want to know. I also I'm already not crazy about the ordering of these, the family, genus, these things all scattered around. So I'm going to do one more step right here. I'm going to say category equals reorder category by n, using the function length. what I actually want to do is say I want them ordered from the, here we go, this is a nice approach. Doesn't make a difference, but I meant to do FCT reorder. This says I want the bar plots with very few categories up here and the ones that make it all the way to 16 later. This makes it a little bit more understandable. Okay, so our data is split. So now we're starting to get a feel for how these factors are set up. We'd say, so I'm going to polish this graph a little bit. I'll do that by doing theme set, theme light. I'll do it with x equals number of collisions, y equals, let's see, y, oh yeah, so actually y I don't need to say anything. So I can say category breakdowns of collisions. That's pretty good. Now, I haven't, this is all, do I want to add any extra information to this? One that I can think of is I want to know how they break down by whether we have a light score or not. If something doesn't have a light score, there's not a lot we can do. So what I'm going to say is, there's plenty we can do, but not for what we're aiming for, which is asking how does light affect whether birds end up colliding with say the McCormick Place. So what I'll do is say fill is NA light score, and I'll throw in a fill equals light score missing. Said light score, count category value. Oh, I neglected to put this up here. I'd say is NA light score here we go. I could polish this a bit more, but it actually does. Oh. Yeah, I entirely neglected to say I need this reorder to happen by some, otherwise the breakdown into categories stops working. It was using median by default. Okay. This is good. So an example of a bit of good news is that, no, not so good news. See, look at this. Isn't this weird? What this is showing is that, McCormick Place, most of the data we have from this building, we are actually missing a light score. So this is kind of the only sliver of the data where we can say birds were colliding at McCormick Place, and we know how many windows were lit. Okay. So that's one thing we learned from this. Other places, almost all birds. What does flight call mean? Does the bird use a flight call? Almost all birds use a flight call. That's not going to be a high piece of information for this data. They're a mix of forest, open. I'm guessing edge is like on the edge of the forest. Maybe someone's going to the city. I'm not sure. And then we have common family, genus, species. I know very little about birds. Passeridae. I'm going to try this out. Passeridae. I came nowhere close to spelling that. New World sparrows, American sparrows. All right, that's a cute set of birds. I hope not too many of them collided. Ooh, a lot of them did. Parulidae. Don't make fun of my pronunciation. I'm just trying to remember it between when I move from one screen to the other. Parulidae. Oh, these are even cuter. These are warblers. Oh, that's pretty cute. Okay, I don't have I don't have much more I can do on the birds. I wonder if is there a data set I can get where we'll get more common names to these. I'm gonna skip that at least for now. This sliver is what's interesting to me for now. I'm wondering about the times where we have McCormick and we have city level. So let's take a quick look at this. Filter not is in a light score. All right. And Oh, I neglected to say stratum. Most of these were on the lower, lower floors? Ground low, canopy upper. Most of the collisions happened on a low floor. Okay, and looking through. Okay, I was going to use a flight call. And so like I said, not too useful. We can look at the locality. We can look at the species. All right. I'm thinking about what kind of model we might want to build. The simplest variation I can think of is imagine we compared in a given night collisions between Chicago as a whole and McCormick Place. I'm wondering then how many collisions are there a night. Start with count. I'm going to say filter for only when there's a light score. How many are there? Count date. Now I can show, like, here's how many there are in a day. It's one of these, maybe log normal, hard to tell, where you have a big peak near the bottom and then it kind of stretches out for a long tail. X log 10. No, not really log normal, or if it is, it might be a shape like what we call a Poisson log normal, where it's a log normal that's low enough that it ends up getting dominated by some random effects. So this it's a shape I've seen before. It would have been cleaner if we were like, always centered around 12. But it looks like there's many nights when not a single bird seems to collide with a window. I wonder if we can get weather data in here. I'm still pretty early on, and I'm feeling tempted by that. But I'm going to start with this analysis first. What I'm going to say is count by, we have date and we have locality. Oh, that's actually something else that splits these up. If I say fill equals locality, here am I going to see a very different shape? No, not really. If I do density and change this to color equals locality, so in Chicago as a whole, we do have a taller distribution. That makes some sense. Notice that if no birds, it doesn't warn me about, there are no zeros in this data set. There's no times I can say. Well, of course there's no zeros in the data set. I'm counting actual collisions. So there are nights where there are no collisions. We don't see them here. Okay. All right, so that's me finding out a little about the distribution. I think if I'm going to do anything, you can do a Poisson regression on this data. You can also do a negative binomial regression. I think I probably need to do a negative binomial regression if I'm going to be predicting how many collisions happen in a night. If we get to that, I'll describe some of the stats behind it. So I take my birds. Here we go. I want to know some things about the light score. What's the distribution of that? And does it stay in place for long periods of time? If I say light score, we have it for, I actually meant to do it on, I meant to do it, as by collision it could be worse, but I meant to do it by distinct date and light score. So we have it for 2,300 nights. Looks the same, great. The distribution is that sometimes we have very bright, sometimes we have very dark. What I'm curious about is, for starters, does the brightness correlate positively or negatively with the number of birds hitting it? I know very little about ecology, but what's called ornithology, but I would guess that the more lights are on mean the birds are unlikely to hit it. Maybe they get confused by the artificial lights, so I don't actually have much of a prediction going in. So what I'd start with is say group by date and light score. I'd filter for light score and for I'll filter for light score and I'll filter for locality equals MP. So that gives us 9,000 collisions. So this gives us a number of collisions, and we're curious, how does it relate to the light score? We have a couple hundred. How many days do I have on each? For each, if I asked, I think this will actually be pretty similar. ungroup. How many days do I have for each? Exception of 8, where I only have 13, I usually have a solid number of collisions. What if, a solid number of days. These are number of days. So I could say, here's a way I could start by looking at this. This is by day and only at McCormick Place. Am I saying McCormick Place? Right, McCormick Place. I could group by the light score, say, is it brighter, is it darker, and summarize median collisions. Here's a start. The trouble with median is that it'll always end up at like a round number. So what I'm going to instead do is a geometric mean. Geometric mean is really handy. Notice it's like 2, or it's 4, or it's 3. Sometimes it's exactly in between 2. It's not great, really. It's not very meaningful. Instead, what I can do is use geometric mean, which is the, what is it? It's the exp of the, exp of the mean of the log of the collisions. Why am I doing that? I'm doing it because of this histogram. Nope, totally different histogram. That histogram looks fine. I'm doing it for this histogram. Number of collisions per night, because I know that there are a lot of low numbers and a few very high numbers. If I just do a regular mean, the high numbers are going to drive everything. Whereas if I do a median, you notice it's going to be 1, 2, or 3, or 4, but it's not going to have the precision I want. I want something in between that is well shaped, well suited to these highly skewed distributions. And geometric mean is a good example for that. I have an extra pipe somewhere. I have some step that's not quite working. Do you see it? I don't see it. I see it now. I think I was missing a parentheses. All right, I like this graph. Collisions, nights. So what this shows is for all the nights on which there was a light score of 3, which I'm going to remind myself means higher, more light, so less light. Less light, fewer collisions. So I could actually plot this. I haven't even done a statistical model yet, where I say light score. Nope. Light score explaining median. I call it median collisions. I'm going to call it average collisions. And I'll say y equals geometric mean of the number of collisions in a night. Did anyone catch the mistake that I made in thinking that we can, I haven't done this yet. I haven't saved yet. Anyone catch the mistake that I made in assuming that I can take the average, even the geometric mean of this data? Problem is, I'm dropping the zeros, completely ignoring any night where there were no birds. So there's a couple ways I can fix that. The way I would think of, let me see, here it is. I need to include light score. All right, I think the way to do that, okay, that makes sense. All right, I was thinking of this a little bit wrong. Not wrong, just realizing there's an easier way to do this. I can take my group by, not this one, by day. What do I got? By day. I can drop the MP, and I can left join it with the light score data. To do that, I need to remind myself what the range of the light score data is. So what is it called? It's called MP light. Maybe this was why they kept the data sets separate. The Tidy people kept the data sets separate, which is, I think, a good idea. So I can join by this with date, but I just did a left join. I actually meant a right join. I mean that I actually want to have cases filter is NA collisions. So these are moments, these are days that we weren't able to find corresponding data. That is, we weren't able to, where we found no bird collisions. And yet, summarize min date, max date. Just quickly checking the range here. It's always a good idea. If I look at this and I look at, say, bird collisions, filter locality equals MP. So we actually, this is really important. We stopped, we would have thrown in a lot of zeros after this point. So there's actually, there's a complication here, which is we don't know if the data is even being measured till after this point. I was hinting at that with some of the earlier histograms, but it's really important to find here. I can say filter date less than max. No, I'm just gonna put it in 2016, 11, 13. So I can now say less than or equal to. So what I can now do is say arrange by date. Oh, and let me throw in one more step. Replace NA list collisions equals 0. Now I can say arrange by date, view. And we're going to see zeros as we go through. With the 9th through the 10th, there was a 0. Some days just don't have bird crashes. We had to deal with that carefully, like really carefully. If we skimmed and we didn't notice that the light data went farther than the collision data, we would have we would have completely we would have ended up with a lot of extra zeros in our data, which is really bad news. Okay, so so now that I've added that, I can retry geometric mean, but I also cannot. You wonder why? Because the log of the number of collisions, if the collisions is 0, is negative infinity. So I need to do log collisions plus 1. This is a common trick. What I say is log of collisions plus 1, and then I subtract 1 once I've got the average. Notice how much better that looks. By better, I mean shows a smoother trend. So this shows like, I think because the zeros are meaningful, days when no birds end up colliding are meaningful. And what we're seeing is, here's our light score, here's our geometric mean. And this I can tidy up a little bit. Light score higher means more lights on. Geometric mean of number of collisions with McCormick Place at McCormick Place. Higher means more lights on. All right. Title. More brighter lights mean more lights at McCormick Place mean more bird collisions. I'm going to say correlate with more bird collisions. We haven't proved causation, but it's definitely pretty interesting. So what I'm saying is, on average is a funny thing when you work with geometric means, but it looks like you expect like less than a bird to die at night, to collide at night, when the lights are pretty dim, and maybe more than one bird to die when the lights are bright. All right. So I actually think that's really interesting. When I see a graph like this, though, I really wonder. I see some waviness. I need to add confidence bounds. For geometric mean, there are ways we can add the confidence bounds for geometric mean. Particularly, we know that this is we could guess that this is Poisson data. We could make a few assumptions, or we can bootstrap. It's pretty popular to go about this with a bootstrapping approach. So I'm actually going to try that, and that lets me remind myself how to use the Resample package. First, how to reinstall the Resample package. Is it Resample or rsample? I'm going to find out the hard way. All right, it's been a little bit since I used this. This is a package, let's see. I think I am thinking of the wrong package. Oops. I meant, oh no, I meant rsample, and I'm replacing Bootstrap. Oops. Sorry about that. rsample, Bootstrap. Bootstraps. Yes. Yeah, yes. That was what I was looking for. Okay, so what is bootstrapping? I don't think it's actually come up yet in one of these sessions. And like I said, it's good. I've used this tool before, but it's been a little bit of time. It'll be a chance for me to practice with it. So bootstrapping is when we don't know necessarily what distribution our data takes. I'm fairly confident that it's an over-dispersed Poisson, maybe a negative binomial, but that takes a little bit of a hassle to do some estimations on. I'm going to, and we don't know that that's exactly the distribution. I'm going to play it a little safer. What I do is I resample. So imagine I've got all this data. Let's start just with one. Imagine I've got all collisions light score equals 3. I have 291 options where that's the case. And I have my distribution of collisions. This is the distribution of collisions when the light score is 3. I ask myself, what if I had run this experiment again, how different an answer could I have gotten? I can't literally rerun time. I can't go back and watch the birds fly at the building again, but I can resample from what I have with replacement. There's some great mathematical rules that say that as long as you resample with replacement, like pick one, then put it back, pick one, then put it back. As long as I do that resample with replacement, it ends up being very similar to as if I'd run the experiment many times. That's the insight behind the bootstrap. I'm not going to explain it deeper here. It's definitely a really interesting idea, and I've thought of doing more writing about it. What I'm going to show is I'm still sticking with light score equals 3. It just makes things a little bit easier. What I'm going to do is say bootstraps. And I'm going to quickly remind myself how that works. Yep. Times equals 100. Why not? I just created 100 bootstrap replicates. And now I can say, let's see, for every single one, what I want to do, so if I took the first one, if I said poll splits, well, how would I do this again? Pluck 1 would actually be a way I can grab this. What it says is it ends up doing this represents a resampling of that data set. What's the 103 in there? I'm actually not 100% sure. And, but it's sample splits. I'm actually going to save this for a second while I remind myself. All right. Bootstraps. If I say BS over bootstraps splits 1, what can I do with that 1? I can get the raw data, but I can also get the, where is it? There's a whole, get the data from 1, but I'm always just getting the raw data. What is it? There's a function. It's funny to me that it's not actually using it in this example. Oh, I guess I do as data frame. Right. So if I do as data frame 1, twice, what I'm getting for every one of these is a sampling with replacement. So if I take this and I take the geometric mean of collisions, I take the mean of collisions each time, it'll be different. It's resampling from the same population. But I can also take the geometric mean. I'm doing geometric mean enough. It's kind of nice to keep it in a function. I don't think there's already one in R, but I'd love to hear someone correct me. So I'll do exp of mean of log of x plus 1 minus 1. Got that right? Take the log to get out of the log transform, do the mean, and then adjust before exponentiating. Okay, so if I take the geometric mean of this is the geometric mean of the first one, of the second one, sample of the third one, and so on. And now I feel a little more confident. Is what I can do is say mutate statistic equals the G equals map dbl, grabbing out doubles, from splits of this. Except instead of this, I have a dot. Yeah, it took me a little practice to remember exactly how we grabbed it out, but here it is. This is 100 Bootstrap samples. Every single time it'll generate a different a different geometric mean. So in this one, we picked a few of the rarer ones. It was a low geometric mean. Here was a high geometric mean. And this gives me a feel for the variation. Like already, I can tell that it's not going to go outside the range 52 to 57 or so, 0.52 to 0.57. I could create a histogram of it and see, like, usually, yeah, 0.51, 0.57 is kind of where it usually stays. So I take this, this would be one single statistic. Solid. What I can do for this one, by day MP, I don't just want one light score. I want all of them. And I'm thinking for a moment how to, does it matter that you can sample more in one than another? Yes, it probably does. Okay, yeah, I know how I'm going to it's probably the right way to do it. All right, I know how I'm going to go about this. There are a few ways to go about this. I'm going to unnest it. I'm going to nest splits as data frame. It's actually going to make the data a bit big, 282,000, but it doesn't really hurt a lot. After unnesting, I'm going to group by the Bootstrap ID and the light score. And so I've randomly sampled random nights with replacements. Some nights will never appear, some nights will appear multiple times. Then the light score and the collisions always stays together. Then I'm going to say geom mean I'm going to say average collisions equals geom of, geom mean of collisions within that sample. So now I'm seeing for every single, watch this this setup, I can say for every single light score, which I'm going to quickly treat, no, I'm not. I'm going to say for every light score, graph your average collisions, bootstrapped, into a box plot grouped by light score. So what this shows now is that there is some variation. There is some amount that we could be getting it wrong based on the natural variation that pops up when we resample with replacement. And this box plot shows, like, at low light scores, maybe there's not a ton of variation. I think largely because there's so many zeros. And zeros, when you have lots of zeros, your variance tends to be low. And up here, there's a good deal more variation. This all comes naturally out of the Bootstrap. We didn't even need to assume a particular distribution. So what I'm doing, so this is handy, but I actually need to group it, to aggregate it at one more level. I'm going to say Bootstrap low is quantile average collisions 0.025. Bootstrap high equals quantile average collisions 0.975. So I'm using the rsample package to get Bootstrap intervals for each of these. Notice it was really not all that much code. If the data were a lot bigger, this step would have been a bit of a hassle. I'm going to increase the number of Bootstrap replicates. So I'll say Bootstrap CIs for confidence intervals. And now that I've done that, I can take the my original data, I can make this graph, and I can throw in an extra this graph. Let's see it one more time, and I can throw in geom ribbon. Ribbon will be AES Y min equals Bootstrap low, Y max, Bootstrap high, alpha equals 0.25 to make it transparent. Oh, forgot one really important step. Data equals Bootstrap CIs. We created the confidence intervals in a separate step. Could have done it a little bit differently. This worked. Yeah, one thing is I need to say ASY. I need to say average collisions only in the line level, otherwise the ribbon is going to be confused by it. Here we go. And now this is the perfect time for a subtitle to say yeah, so this is a perfect time for a subtitle to say what is it? Yeah. Ribbon shows 95% percentile bootstrapped. I take it back. Bootstrapped percentile confidence interval. Why do I say percentile? Because there are a few other methods of going from bootstrapping to confidence bounds other than taking a particular quantile. I happen to like this one. It's one of the simplest. It's worth mentioning. This gives me a lot of confidence that there is an increase, but it's not a statistical test. So this is definitely interesting. You know, here's another interesting thought. There's I'm deciding between two ways I can go. One way is I can try doing a statistical test, such as a Poisson regression or a negative binomial regression to predict the number of collisions. Another way I can go is to consider there could be confounding factors. Imagine for a moment that during the here's an example. Imagine during the summer you don't need as many lights on, and therefore, actually that's a big one. In the summer you don't need lights on, and maybe that because the sunset is later, so maybe that means that fewer birds hit buildings. That's a definite possibility of a confounding factor. I could think of other ones that might have to do with weather, visibility, certainly time of year. The place to start with that is I have two approaches. I'm actually going to dive into that because I think it's really important. At confounders, you really want to always be thinking what could be confounding my analysis. And one that you could do here is take a look at your bird collisions. Count by month equals floor date month, and count them by month and locality, and ask if there's a variation by time of year. So say month and color equals locality. There's an enormous, that is confusing how much there is an effect. 2000, start at 2000 nope, I might be wrong. Oh, instead of counting the total number, the Chicago as a whole, wow, those are spikes. What are those spikes about, those regular seasonal spikes? Makes me wonder. Really makes me wonder. Maybe it's migration season, most likely. Huh. That probably needs to be controlled for. That's actually interesting. I didn't actually think of that. We have data mostly since 2005. I'm actually going to do it since 2005. And then instead of counting by floor date month, I'm going to get the month. Label equals true. A month of date. Label equals true, and ask how many are there in each month. I need a group equals locality to make this graph work. Are we always missing data on January, February, and December? Or are there just never collisions because birds have migrated south? It's weird to me that there's literally never. I would not have expected that. But yeah, what we are looking at is that there are big peaks in May, September, and October. So that's a big confounding factor. Really worth knowing. There are a few ways we can control for it. A really simple one is we do an analysis like we did above, only within September and October, or only within one of the other months. And we try saying like, we just segmented this section. Another way we could do it is by trying to bin this by time of year and use that as a regressor in a statistical test. We could do both of those. They're all interesting. I'm going to take one slightly different strategic approach. What I'm going to try is this. Notice that they gave us Chicago data. They didn't just give us the MP data. MP we spike in September, October, but whatever affects birds based on time of year or weather or other factors like that, presumably would affect birds as a whole in Chicago. So one of my questions is, how does the number of lights that are on in this one building, McCormick Place, that is correlated? If it turns out that's highly correlated with ones in Chicago as a whole, then we know, highly correlated, then we just know this is a confounding factor. This is time of year or weather or something like that, something that affects both the number of lights that are on and the collisions. But it's harder to think of a case where we'd say that that the number of lights on affects collisions with McCormick Place, but nowhere else. Nowhere else in Chicago. So I'm going to repeat this same analysis, and I'm just going to add a couple of group bys. Where's my group by? I do a filter here of locality equals MP. I'm not going to do that. Instead, I'm going to say, starting to think I could do it. Nah, if I do not as an A light score, I'm already in the right range, 2000 to 2016 or whatever. I'm going to group by both date and locality. Right join it. Yeah, we have an issue here, which is that, yeah, once we've right joined it, I need the date to be complete. Oh, okay, I can do that right here. What I can say is complete date and locality. And fill equals list, collisions equals 0. So what I need to do is ensure that any day on which we have collisions in one but not the other, complete is a super useful tidyr function. Any day on which we have collisions in Chicago but not MP or vice versa, wow, these really differ. Any of those we would need to include them at this point. So I'd say bird collisions, light score, all Chicago. Okay. What does this look like? Filter locality equals Chicago. I'm a little worried. Yeah, why do I have so many zeros in Chicago data? Didn't I look at that histogram earlier? Thought it looked more outward. Let me see. Can I see that histogram? Can I jump back to it? By outward, I mean I thought it looked like the collisions in Chicago were higher than collisions elsewhere. We have too much going on to look into that. All right. So now I've got a group by day and locality. If I want in here, I need to say group by light score and group by day MP. This is what I love locality. This is what I love about the tidy bootstrap approach set up by Max Kuhn and others in rsample, is that you can just add one group. I thought we could, but light score. Oops. Left join, right join with MP light. I forgot a pipe. You can just add another column, and now you've got your bootstraps for these. Now, why is locality sometimes NA? Why is locality sometimes NA? I have a sense why, but it's a little bit annoying. All right, the only thing I can think of that kind of fixes this is if I add locality. I'm not happy about this. This is a bit of a hack. This is not quite doing things the way they would typically be done. What I do is ensure that every MP light has both a Chicago and an MP. And I join by both date and locality. All right, so now the data looks a little cleaner. It always has. So what I'm doing is making sure that every light has a Chicago and MP, and by joining that, I think I can find myself in better shape. Okay. Perfect. All right. So I got my confidence intervals. I throw locality into here, as well as into my geom. I can add it to both. Color equals this. Does this work? I think it might work. There it goes. Okay. So what this shows is that the light score at McCormick Place does correlate with the number of birds, number of collisions, and to remove with McCormick Place, and not collisions in Chicago overall. This is helpful. So that's why we have some overall Chicago, at least it's one of the reasons we have overall Chicago data as well as McCormick. They say geometric mean of the number of collisions at there, not with, and color location. I don't like locality. All right, this ends up our without doing a statistical test, they do some statistical rigor. We notice that that if it were a confounding factor having to do with something like time of year, you would expect the light score at McCormick to be correlated with the overall Chicago. It is not. It is correlated with bird strikes at McCormick Place, and I can put in a let's see, McCormick Place, Greater Chicago area. When I do something like this, I'm gonna drop this and say, I want locality. I want locality to just be different at this point. I want to say mutate locality equals if else locality equals Chicago, then Greater Chicago. Otherwise, McCormick Place. I like to have more helpful legends. All right, and this is my not Chicago. So I wanted to try and fit this into a good graph. So this was my approach to seeing how do bright lights at McCormick Place affect the number of bird strikes, and it looks like the brighter the lights, the more birds hit it. And as I said, we looked at confounding factors. We tried controlling for confounding factors by comparing it to the overall Chicago distribution. We could have done this with a statistical test. We could have said, entirely have said, let's use this would be a regressor. We would have probably done either a Poisson or an over-dispersed Poisson regression, such as a negative binomial regression. Almost certainly a negative binomial regression now that I'm thinking of it. And it would have said, we would have said, yeah, how does the, we would ask if it affected it significantly. We could have asked whether there's an interaction term between these two populations, Greater Chicago and McCormick Place, to really make some statistical conclusions. Having said that, from what I've seen here, I feel like I'm happy making this this conclusion. If I had a little more time, we'd do a negative binomial regression, discuss what it meant. But I don't like to rush those, and I feel pretty comfortable with this. In the meantime, I got to remind myself how the bootstrap approach works. These really just two pretty handy lines, and I could have set it up a bit differently to be faster, but yeah, I'm really to be more computationally fast. That is, these couple lines really got us a long way in terms of our in terms of approaching statistical tests in a tidy way. So, I think I learned something about birds. I wonder, was that the conclusion that Winger came to? They said, well, the influence number of varied across a set of species. Ooh, I completely forgot to look at across sets of species. Well, I'll look. Maybe others will be inspired by this analysis to take a look across sets of species. And you certainly would want to use statistical tests like regression. Okay, Well, I had a great time. Thanks very much for joining me, and see you next week.